So when, as they say, we're on. Let me just flip these round. So, welcome to MP3672 Engineering Simulation. In this module, I don't try to show you that engineering simulation will solve your biggest problems. I don't try to show you that engineering simulation is the answer to all our problems. And what I do try to show you is the limitations of why it isn't the best and the only thing to do. Engineering simulation in all concepts, be it computational fluid dynamics through to finite element analysis through to dynamics of a particular assembly, will always minimize the cost when it comes to the step between design through to prototype. Obviously we've been in a conventional world at one point where the only way to really get straight answers was to build a prototype. What this is really about is trying to consider your simulation, minimizing the error that you're producing, and then moving towards a big solution. But that solution will only take you to building a prototype which is more than likely going to be successful. I say more than likely because most of the time it can only be, depending on the system that you're simulating, it can be varying between 80 to 90% accurate. It will never be 100%. Well, it will never soon be 100%. I'm sure one day someone will solve it and get perfection every single time. Every single simulation I've ever run to do with the exoskeleton stuff we've been doing always drops out an error. And it's the error between the test and it's the error between small things that missed. Like, for example, recently we simulated 3D printed materials looking at the neck and its weight against the material itself. When we simulated it, we got 0.1 of a micron of displacement, so it deflected in that amount. But then when we tested it, it was almost double. It was almost 2.2 of a micron. And what we suspect that is it's our version of the material that we were using in the simulation wasn't an accurate representation, and also the interboundary layering between the two, we chose to neglect it because it was so small. But that is just a typical example of where simulation gives you a very close answer, but it's never 100%. What we will be using this year, we will be simulating with COMSOL. This is COMSOL Multiphysics, and we will also be using another FEA package. Now, as I'm going through, I'm going to explain to you what makes this module different this year and how it is flexible. For the dynamics side, so apologies, so on the first side with COMSOL and the other FEA package, we will be studying finite element analysis. Our predominant aim is to study the static behaviours and look at the meshing procedures behind it. My aim is to show you what is the most important thing within a simulation, and it actually is the meshing procedures. Got to think of it that if you have two nodes where these points, if you will, I mean, one of the best representations I ever heard of a mesh is a spider's web. If you put your finger onto a spider's web, the rest of the system starts to elasticate, and it will move in that particular way. Now, a mesh behaves the exact same way. It essentially wraps your geometric representation, and then what you get is an elastication which is based on linear behaviors. We will go into much more depth than that, but that's just a very crude summary of where that is going to. Secondly, we will be simulating using SimMultibody with MATLAB, and also my weapon of choice will probably be SOLIDWORKS simulation. SOLIDWORKS Motion. SOLIDWORKS Motion uses some solvers by a company called MSC. They actually use MSC solvers by Adams. We will cover that more into who they are, what they've done, and how they are one of the biggest solving companies in the world. Now, I am not going to force you to do two softwares. I am not going to force you to learn two softwares. What I thought this did is all sessions that run, you'll notice on Teams you've got links to both of them. The way that this is going to run is I'm going to let you choose which way you want to go. On Wednesdays, we're going to do the MATLAB. On Thursdays, we're going to do SolidWorks. Today, we're going to just have a bit of a warm-up using actually just Excel. We're going to solve a very common problem, and we're going to get a nice solution with that. The other thing that I wanted to point out is, as this works, I have been asked to take attendance. So, all these videos are recorded. All these sessions are recorded. I'm always open for discussion about whatever it is that you're wanting to learn, if there's anything for this, anything that you're struggling with. So what I mean is, let's say for argument's sake, you start learning SolidWorks and you go, nah, it's a bit naff, is this? I'm not a fan. You can go back and look at the other session that we did, which was using MATLAB, multibody, and you choose which you want to do. What I mean is, when it comes to the assignment, I'm actually going to set the assignment, but you can choose how you solve it. It's a little bit more flexible, and it's a methodology that, to be honest, I've never done before. And I wanted to try it out because we're online. We're flexible. We've got all these different things we can do. And I wanted to give it a go. So, when it comes to attendance, now I didn't realise, a friend of mine showed me this, I didn't realise that Teams is brutally accurate when it comes to attendance. So, now we cannot put groups. Now, I know that the university have tried to put everybody into groups, specific groups, which, you know, I understand. But what I'll be doing is, during the meeting, during this, I will right click and I will just snapshot the attendance. So what I mean is, when it's submitted, it won't matter which one you came to, at least you came to one. Again, offering this more flexibility. Now, you've got to remember that on the timetable, it will be next to impossible to be able to offer this flexibility as a black and white timetable, because it would be all over the place. So again, if there is anything that you hit as you're going through, please get in touch. If there's something that you're not happy with, again, get in touch. I can change this. My main focus and aim with this is to give you the best experience that I possibly can. Again, because it's new, your feedback is very valuable. So, I'm Matt Dickinson. My email's down at the bottom left. And at the bottom right, for those of you who know Tony Broad, you'll know that me and him share an office, which is CM123. Due to COVID and due to the distancing, we decided what might be a better idea if one of us evacuate the room until we get a bit more clear. So what I've said to Tony is, he take over that office, and I will use another one until everything's a bit more calmer. So when I am on site, because as time goes on I will be on site, you will find me in EIC 214. If anybody's unsure what that one is, that's the one with the exoskeleton in the window. That will be what I'm nicknaming my running office. If you are desperately needing to get in touch with me, please just get in touch through Teams. What I'm finding at the minute is it is a very, very efficient way to just ask a quick question of, this doesn't work, what's this, I don't understand that, and then speak to me through that way. I don't mind if you're free and I'm free, we can even have a quick call, because I do find that a quick call can solve what would be a series of 50 emails. The other thing is as well, when it comes to my emails, if you do need to email me, try to title your email MP3672. I've written in some filters onto my email to try and sort things for me, because if I don't, I can end up with around 100 emails a day. And it's frustrating, because it can be, come and buy our product, this is really good. I don't want to buy anyone's product. So what can happen is you can get lost in them, and it frustrates me an awful lot. So if you do need to email me, title your email MP3672. If you'd rather just get in touch with me through Teams, again, get in touch with you through Teams. I can discuss anything. If there's anything, again, that you're not happy with, let me know, because I want it to be an awesome experience. Because I am quite passionate about simulation, as you're probably going to learn as the year goes on. Right, so back to the actual point. We will be studying FEA, finite element analysis. We will be looking at Well, one thing that my lecturer always quoted when we were in the classroom. The thing is, with FEA, if you put crap in, you will get crap out. The amount of times that you'll meet people who go, oh yeah, I'm a very good FEA guy. I can do this perfectly every single time. They are the most dangerous people I must have ever met in my life. They're kind of the ones who try to convince you that their approach is flawless, they know exactly what they're doing. But the truth of it is, if you set up a poor simulation setup, if you put in boundary conditions which are way outside of what it's meant to be, you can produce a set of data where people look and they go, oh yeah, any good that? And it can be completely out. So in other words, you can be fooled dead easily. Dead easily. What I intend to do is we're going to go through some verification methods. Now, one thing to keep in mind, and I will keep stressing it to people, if you verify, you take something like a simulated model and then you mathematically match it to figure out what the error is between the simulated and the calculation. If you validate a system, what you've done is you've manually calculated, you've got that simulated model, and then you've tested the real thing. The amount of times I get in projects, well, I validated the model, you kind of go, no, you've not validated it, unless you've got a big, because I can end up with aircraft parts and all sorts. You kind of go, not convinced. So try to keep them two separate. I know it's only terminologies, but with terminologies they can lead to two massively different things. So try to keep that in mind. But as we're going through, I will always reiterate, make sure that you refer to the two things. I have been just as guilty. I think one of my assignments last year still had validate written on it, which was totally wrong. Because I still get myself confused here and there. But that will be our systematic approach that we're going to take. Now, the example on the bottom left actually is an example that I found. Now, some of you may be too young to know this, but Marin, the mountain bike company, one during the 90s were amazing. I've only recently just got back into biking. I've not come across any Marins. I don't even know if they still produce. But Marin were amazing. They approached a particular FEA company and said, look, we want to do a simulation and we want to be sure that the material we are using is a good representation. This said company came up with an amazing technique, and what I thought I'd do is steal that to show you that process. So this is going to be one of the genuine notes that we work through. Predominant focus software that we'll be using is COMSOL Multiphysics. For anybody who doesn't know who COMSOL Multiphysics are, they are the sister company to MATLAB. If you've never touched MATLAB, do not worry. It comes very aggressive. Well, it comes a little bit non-intuitive, but as a software, it is amazing. But with COMSOL, we have predefined typical parts examples that we'll be using. I am using also a second FEA software, so again, you can choose which way you're going to go with it. The other software, the only reason I've not named it yet is I just need to confirm that it's going to be ready for when I want it. But we're going to be using the two because this COMSOL is quite heavily academic processed. So this is quite good for if you're doing very deep R&D, or if you're doing developments for nanocoating materials, or if you're wanting to look at harmonic frequencies in blades, anything particular that's occurring. I use this quite a bit to look at bodies as they're moving with exoskeleton technologies on them, to make sure that the structures that we're choosing do that job. The beauty with this software is we can write some of the all-important mathematical calculations into this software, and then when we run our simulation, we can compare our mathematical solution to COMSOL solution to see how close we get. It's a very unique option that this offers. It's very rare in other softwares, but it is a really nice function that I like in this. The other thing that we will be doing is MATLAB. The back, this is, well, it's actually MATLAB. It's actually MATLAB, Simulink, Simscape, Sim Multibody. Lots of sims in there. What we will be doing is looking at dynamic systems as they're moving in space. Now at the back you can see what was my original KTM engine. I stripped the KTM 525 from what, for those of you who don't know, our manufacturing spot in Wharf. I stripped that and remodeled all components and then rebuilt the engine in this. And with this engine, I was able to look at wear, I was able to look at hydrodynamic lubrication, able to look at combustion processes. I was able to look at nickel carbide as it's against the cylinder walls, because this cylinder in particular is not a sleeve, it's a coated material. And I was able to really go into depths with it. And what this also offered me the ability to do is do live data acquisition from Ricardo, from the Ricardo dyno, and actually feed some of this into my simulations to make them more and more accurate. This gets to a whole, don't worry, for this module we are not going to go to such depths, so don't be too worried about that. But what I want to do for things like this is show you the solid foundations that gets you to that position. And the other example there is the bouncing ball. The bouncing ball's fascinating. So if you consider the mesh nodes that we discussed just a minute ago, if you consider that the nodes, the spots, if you will, the points in where on the spider's web joints will connect, that is what your resolution will be. In between them two, you'll get behaviours of materials and all sorts. If you're doing a bouncing ball, we enter a realm that they call the Hertzian problem, where if that bouncing ball hits the ground, if it's covered in a resolution, if it's covered in nodes, if you will, what you're going to end up with is material penetration between the target, in this case the ground, and the bouncing ball. However, MATLAB takes it more of a dynamic approach. If you know what the coefficient of restitution will be of that material, if you know how it's going to respond to the ground, which we well do, we can model this a different way. So when it comes to hyperelasticity of a material and its ability to stretch around a particular target, it opens things up a bit. So as we're going through this, don't get me wrong, we won't be just doing bouncing balls. We'll be looking at real engineering problems, and we'll be extracting the maths that supports that. And rather than just sitting here and going through countless and countless amounts of deriving, we will be applying that theory. We'll be using variables that we can see in an equation and then actually applying them so we can see what they do. So think of it as engineering mathematics through application. It just seems a bit more used, if you will. The important thing with any dynamic system as well is that we verify what we're doing. We show that it's got, oh, apologies. We show that it's got realism to it, where it fits. Because nobody wants to be told a million times about how things don't work or anything like that. They want to be sure about why they're in particular doing these things. So that's where we'll be using MATLAB. Now, at the same time, the same problems, the same dynamic problems, what I thought I would do is also run alongside with this with SolidWorks Motion. What we can do is we can use it, we can learn to navigate it, we can learn to take a look around it, see how well it works. And then when I present you with your assignments on this, you choose which way you want to go. You choose how you want to solve that problem. Choose one, but choose which one you would rather use. MATLAB Sim Multibody, for those of you who were in year one and sat MATLAB's, Matt Stable's engineering applications, I know you've had to code and code and code until you were blue in the face. However, what this will show you is what you were doing. It will really spell out even more how it all fits and how it all fits together. If you've never done MATLAB before, don't worry as well. My job here is to make sure whatever you choose to do, I support you 100% to get you the best mark that's possible. I just thought by doing it this way, it just offered a bit of variation. And it offered that idea of that we're not really considering software, we're considering the problem we're presented and how we're going to solve that problem. At that same time, what will drop out is a little bit of your frustrations. You will get annoyed because you'll come away and go, this software won't let me do this, won't let me do that. and then it becomes down to you of figuring out what's the best way to solve these problems. So it's a different way of doing it. Again, everyone is welcome to every single session. After all, they can't actually put us into class sizes. We're online. We have an infinite class size. When it comes to the assignment, I didn't spell this out to the guys yesterday actually. In fact, let's go on to the assignment slide. For assignment 1, now because I'm still trying to we've got a new teaching server up and running, and as ever, as with any new software, as anything that's getting set up, there's been problems getting this thing working right. And I don't want this to hinder your experience. No one wants that to hinder your experience. So what we decided to do is, while that's getting fine-tuned and let them just do what they need to do, we're actually going to do assignment 1 in semester 2. We're going to do assignment 2 in semester 1 because we have all this. I'm going to just take a few of you, well, I'm going to show you all as well where everything is as far as Blackboard, because I'm aware not all of you will be very clear about how all this is going to work. Excuse me. And the second assignment for MATLAB Sim Multibody or SolidWorks Motion, if this works really well, we'll see. That is got the weight of 55%. In the second assignment, I do want to see the model that you've built. Now, for anybody who's not CAD savvy, please do not worry about this, because this has left a lot of people feeling very nervous. If you're not CAD savvy, that is not a problem. I am not modelling your ability. I am not marking your ability to use a CAD system. I will present models to you, then you've got to find the solution to these problems. You've got to make it work. So I'm actually marking your ability to model the actual scenario, not the structure itself. So it just puts it into perspective. So if you're not CAD savvy, do not worry. We are not using, you won't have to model anything. If you are, you're welcome to generating your own models. However, in this particular assignment, this second assignment, I will be asking you to submit the model and your write-up to support it. For the first assignment, I actually challenge you to something. The first assignment, we're going to make a miniature research paper. In the first assignment, you do not submit your model. You just submit your report. And the reason that I say this is going to challenge it is because a lot of people can sit back and go, it's alright, it's in the model. If you're not submitting the model, it means that I won't be looking at the model, I'll just be looking at the work, and it's your job to make sure it's reported well. So these are the things to keep in mind, and don't get me wrong, this is not the last time that I will discuss these two assignments, but that is going to be our approach to it. When it comes to submitting it, it will be the normal process, but again, I will take you all through that. When it comes to the server, if you do have a PC that's a little bit weak and it's not been able to support everything we need to, you're all going to get access to this server. I've made a short video. I've made a short video which will show you how to install it, how to get it running. Now, what you'll notice that's different about my classes is I do not use Stream. Again, it's not like I've got a big Microsoft is crap or anything nothing like that at all. The reason I don't use Stream is sometimes the signal can be bad. Sometimes it can pause, it can not go right, it can go wrong. So I end up using Microsoft Expression, which in essence actually records it to my hard drive. The reason I do that is, let's say we get a really bad signal, I don't know it's happened, but I'm still pushing forwards. Stream also records that bad signal, so it goes, it's really frustrating. So what this is it's almost like a backup. So it means that the record that I'm doing, because it's going to my hard drive and not using the internet, it means it's a solid signal all the way through. What I do then is I encode it and I turn it into, I run an unlisted YouTube channel. And I say unlisted because you cannot find it by searching for it. And on that YouTube channel, I upload sessions notes. I turn it into a link, and then you'll find these links on Blackboard. So if you click onto it, if you've already been on there and you're going, whoa, 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 I'm going to YouTube, that's why you're going to YouTube, because I've been using YouTube as a repository for storing these videos. Right, before I take you through Blackboard and just show you just a couple of things, is there any questions about this? 2 seconds, 2 seconds. Okay. Right, the question I just got, can I just say that we can deal with this outside of here? I do appreciate your concerns on it. Definitely appreciate your concerns on it. It's not something I can fix right now, but it is definitely something I can chase up because I can understand why you're a bit concerned. Just to reassure you of anything, normally what I will do on week 1, I know it's not the best way to describe it, but I use week 1 as a teething thing, so almost like a warm-up, if you will. It's just so that if anything's not working right, I can actually get on it and get that fixed. So we're not going to do anything major that you're going to miss out on, but I just wanted to reassure you that there's not large areas with that, but I will get that chased up today, to be honest. I understand what you're saying. So I will chase that up. That's the best thing I can say at the moment. That's a good comment. Good comment, that, Harry. Like it. Yup. 2 seconds, George. Let me just pause, because as I said, I do prefer to run it that way. So, that is the overall of simulation. That is roughly how all this will work. So let me just take you through Blackboard so you're aware of this. Obviously your Blackboard to my Blackboard is going to look slightly different. Onto Blackboard, and I'm going to go MP3672. So on here at the minute, for anybody that's unaware, SolidWorks and MATLAB software downloads, it is all on here for your use. If you do have problems with it and there is issues with it, please let me know. I know that I've just had correspondence with some who do have some problems with it. Again, I'm going to chase that up today because I wasn't aware of that one. On here you will find 2 codes that are put on there. Personally, I have tested this myself. This first code has worked for me for the 2021 version. The one thing I do want to point out, if you are going to install this system, one thing to keep in mind is last year, some of you who are actually on this call had this problem. You went to install it, and then when you installed it, it just said that your license had run out and it sent you all over the place. Really frustrating, and that I do really understand. So I chased this up with Dassault. Dassault claimed that what they wanted to do is try and put a stop on the amount of people who were using their student version and installing millions and millions of times. Not just with us, across their distribution. So they didn't tell anyone, but you needed, when you went to uninstall your software, you needed to deactivate your license. So this year what they've done is they say that they've put in an automatic deactivation button. I've come across millions of these deactivation buttons before. And I've come across millions of examples of that before, and I'm never 100% convinced. I'm never 100% convinced that they work very well. So I would always say, if you are going to do it, make sure that you deactivate your old license before you uninstall it. Because I can see that going horribly wrong and the whole thing happening again. Even though they claim it's an automatic system, I'd say do it anyway. Right, when it comes to MATLAB, follow the account, the licensing center, and then go to the account and then take a look at the download process. So if I go to my account, any minute now. On here, I've got my daft picture, but on here, I can go to one of these. You will be asked to register. You will be asked to join up. I think you are anyway, because I've never done it as a student, that's all. And then I can just choose one of these, give it a minute, and then I can go to download, and these are all the products that I'm presently using. Go to download, and what I would always say to download and install is everything to do with Simscape and Simulink, because it is Sim Multibody that would be centering his attentions to. So Sim, oh god, where is it? Sim Multibody. That's the one to do with the MATLAB side of things. Again, I'm going to try and run it in two separate forms where we try to solve the same problem in two aspects. So yesterday we used MATLAB to script a solution to a really common problem, and today what I thought we could do is actually use Excel to actually build the exact same problem but a solution that way. What I would suggest is, if you are keen to do MATLAB, take a look at that one, and you can either choose to turn up to that one or turn up to this one. Either way, you're welcome to all of these. What I'll do now is I'm just going to take an attendance list. So just make, because I can often forget. So I've taken the attendance list. So now I've got a snapshot of everybody as well. Right. The other thing on Blackboard is module materials. Under my module materials, you'll find everything with it. So live sessions. So I've got both links to both live sessions. If you click onto that, that will take you to the link for Teams. If I go back to materials again, and then if I go to the notes today, I'm going to center around the first order system. And as I said, week one, I do try to keep it as nice and steady as possible, and just looking at different ways of solving particular problems and getting a solution, and looking at getting that answer. As we move, we will hit the ground running even more, but as I said, this week is just to get going and getting clear about how all this works. So under module materials as well, onto recorded sessions, you've got the intro to simulation using MATLAB. So this was yesterday's session that I ran, and if you click on that, that will take you to YouTube. Again, you choose which way you want to go, you choose how you want to do it. What I'm looking for in the assignment is that you can demonstrate a solution for all the problems I'm going to present to you. Before I crack on, any questions on that? I am trying to keep a strong monitor on the direct feed and also the group feed as well. So if there's anything that pops up as you're going through, you're more than welcome to just ask a question however you like. Right. So the first order system. Now I've added this picture about half an hour ago, something like that. This is a cracking example of what I wanted to study this morning. Now in any of these systems, when you're talking about simulation through numerical integration, what this particular system is recognised as is a first order system. The typical first order system will respond with a steady curve and then come to rest. So it's preloaded, it has one particular direction, and there is only one particular motion that it will respond to. Yeah, there's only one particular motion that it will respond to. What we're going to do is we're going to study how this is designed. The key elements about the door mechanism, because that is what this is, it's a door mechanism. The key elements about this is it has two main features that influences its output. One being the spring, the other being the damper that supports it. A spring system is an energy storage method, so you compress it or extend it, and that energy will be stored and is ready for dispersal. Once you disperse it, it will try to return back to its elasticated origin, its easiest state of motion. Then once it's in that position, obviously it's there to be reloaded. If you incorporate a damper into this, obviously damper is a dissipation method of force as it's being applied. So in other words, you can actually steadily control the way that it outputs. So if I show this as a plot, because I'll go up and down these notes are actually on Blackboard. That is the typical motion that you would expect from a spring damper. Spring damper system drone looks like that. So what we're essentially doing is we're applying an initial input to it. We operate with a spring stiffness. We need to know where our first position of Y will be at zero motions, at a time of zero, sorry. And obviously if a system's preloaded at zero, we can presume that that Y position will be sat at zero. And the C value being the damping coefficient. So that's what these layouts are here. Now, to equate that, we use a static sensitivity. Now, the static sensitivity is the same as the gain of a system. So the static sensitivity is output over input, as to any gain system actually is. Now, in these types of motions, unless we know more and more about the mechanical system and how it's behaving, what we actually do is presume that this static sensitivity is equal, that it's actually being used at 1. So that mechanical efficiency between the input and the output is assumed to be perfect, unless we know more and we can tune it. A lot of the times with the variations between that static sensitivity and its normals actually are very, very small variations. But for those of you on motorsports, when you step into level 7, so your final year of Masters, Graham will take you through even more about the static sensitivity and the gain of it, and how it affects, and how through things like hydraulics these systems can change a lot of an output. Excuse me. So initially in these states, what we always need to try and do is establish what a velocity for this type of system will be. Again, all I'm actually describing is my door mechanism. I'm just looking at the door mechanism, not looking at the door itself. What I'm going to do is presume that the door is opened, and we're going to provide an input from that door being opened. We'll keep the numbers as straight as possible, so we will keep them as straight integers as possible, and just to keep the layout as simplified as possible, and then we can tune further to actually have a look at what happens and why it's actually happening. Right, so to solve this, let's just pull down to the notes a little bit more. What we need to do is study 3 separate elements of this. So S, again, the sensitivity of the system, our initial input. Our time constant is a mechanical variant based on the damping and the spring stiffness, known as the time constant, and obviously C and K being damping and stiffness. For a first order system, the zeta value does not apply in this case. Zetas you'll find it, for anybody who doesn't know, zeting is a damping coefficient when you rise to a second, third, fourth, fifth or sixth order systems. For anybody who doesn't know as well, a system can be referred to as only a system because these types of behavioural things can occur in all different things, from electronics through to mechanical. Those of you who are on CAE, you'll know last year that you did EL2104, which was studying instrumentation and control. And on there, you and Bogdan will have shown you system outputs, which represent these types of things. So one of the reasons that CAE students do this is to have a clear understanding of the order systems and how they behave. Right, so as I said, yesterday we scripted this. Today I wanted to actually present this in a different format. We're going to use something dead straightforward. We're going to use Excel. Excel gets a real bum rap. A lot of people think that it's not really used anymore, and I've come across many times where people have generated very key simulations, very key particular outputs. I know Graham on Motorsports, he's used it quite a bit, and it is still a tool which is heavily used, as much as a lot of people would argue differently. The other thing I should point out about these sessions as well is it's going to be less and less of me just rabbiting on and rabbiting on and rabbiting on. When we hit the ground running with this, what we will do, we'll spend the first hour me discussing about the notes and discussing about what we're trying to learn from these notes, and then the second hour into that I'm going to let you try and dissect a little bit more, and what I'll be doing is almost coming off, and then I'm open to discussions, well, private discussions I should say. And so if there is any comments as we're going through, you're going to be welcome to get in touch with me that way. I figured it just might really help that way, but again, it might not. Just need to test it and find out. So, getting down to it, I'm going to go to my, I'm going to open up a new Excel, an Excel spreadsheet. So again, we know that we need, so look, we're going to need a damping coefficient, we're going to need a spring stiffness, we're going to need initial input, we need a Y, of course, yeah, we need a Y. I don't think I put that on there. I've not. We need a Y position, which is indicated here. So we need to know where our Y is going to be. And if anybody's never used Excel like this before, I'm going to go dead steady with this. So first things first, I need damping. And COEF. So under my damping coefficient, just to make it easier for reading, I always like to put in what exactly it is that we're looking at. So I'm going to make that 1. I'm going to go spring stiffness. Again, what I'm essentially doing is just designing around that first order system. So what I'll do is say K is equal to 1. Going to go input. Now this will be our initial input. So what I'm saying with this is that this is, so let's say the door has been opened to its angle, then the piston that moves along the mechanism itself loads the spring. That's why, even though I referred to it as a door, if we just quickly refer back to the actual diagram, not diagram, the picture of the actual mechanism, you can see there that it moves linear along its axes, and it's just conversion. So we're presuming that the input is going to be loaded by the door and we're responding, so we're concentrating on this mechanism. Then we'll go 1. We're going to go initial conditions. So we're going to go initial conditions of Y0. Whoops, Y0 is equal to 0. So this refers to now. I've had students argue with this to me for years. So anybody who wants to argue, you're more than welcome to. At 0 seconds, it's saying that the initial position of our mechanism will be at 0. because at zero conditions it's not moved anywhere. I've had students go swear blind that it should have moved, and I don't know what we're talking about, and yeah, it's been a bit hilarious. Right, so because we're using an iterative state, now to just come back to the notes, what we essentially do is we have a variable of y. In this case, our initial y position is going to be 0. In essence, we're setting it at 0. Then for time, which is t, it's going to take iterations. Now there should, whoops, that was me, apologies. Now you can see there, so what we do is we put an iterative point here. We do 2 points and then join the 2 together. This is very, very similar to the meshing procedure methods that we use in FEA. So what we're essentially doing is joining these 2 together, and then by calculating out velocity, so it's obviously speed over time, a distance over time, what we're actually doing is we're trying to predict our net steady state. So we've got our dy by dt, so that's our initial first process that we do. Then what we can do is we essentially say that the new position of y is wherever it formerly was, multiplied by our initial time step. So we're gonna choose an iteration, how many times we are recording the position of where it's sitting. If we make this too big, it just won't work. In fact, what we're going to do is do that to see what happens. But if we make this too big, this will become massively unstable, and the equations just won't seem to work anymore. This, by the way, is using Euler's method, Euler's method, whichever way you want to say it. And this is a very common approach to just ideal first order and second order systems. There is a second order example on Blackboard which you're welcome to have a crack at. Now I put that on there for anybody who's very enthusiastic to have a go at it. Then once we've done that, we can then move on to the next predicted state. But in Euler's method, he also presented something which was very good. He presented this. This is what he nicknamed the exact solution. Now what we're using here is a very truncated method. It will only ever record points in space. This is a much more exponential process. It actually is a different way of doing it, and what I'm going to center on is the iterative process. If you build in the exact process, well, in fact, let's get to that in a minute. So let's get back to where we were. Right. So from there, we're going to do a time step. So I'm going to randomly choose a time step. 2 seconds. I've had a great question. Great question. Will we be using a lot of iterative methods in this module, or just Euler's method? So in this module we will actually be using quite a few different ODEs. We will be using, there's about 45 different options. My personal favourite and one of the most common ones, big use throughout dynamics, is Runge-Kutta method. Runge-Kutta comes up quite a bit, but there's also other little good ones to use as well. During this, it won't be, this is the first and probably the last time that we will concentrate on using Euler's method. Using Euler's in this case is just a way to get people thinking about addressing an equation and then using it, just because it's a nice process to, in essence, warm up to the module and what we're going to be doing. So my best answer is yes and no to just Euler's. That's my best answer. Right, so I'm going to define a time step. For my time step, I'm going to define that as h. From there, I'm going to define my time constant. which in this case is tau. So constant TAU. I put that in. Just I know you can put symbols in. I've just typed in. At least then I know exactly what I'm talking about. I'm just setting them all strict at 1 at the minute. I'm going to tune them all up a bit more in a little bit. And then my static sensitivity. So static. Is uppercase S is equal to 1. So what I'm going to do is I'm going to put a board around that. What I've always done, personally I've always done, is always to put borders around to tell me where constants will lie. This is my system and this will be my constant as I'm going through. These won't ever change. However, as I'm running through with columns, this will change more and more and more as I'm going through. So, oh, excuse me. So I'm going to go H. Now H now, this becomes the iteration of everything that I'm doing. So I'm going to go equals. In fact, really, this wants to be 0. Because what I want to do is now set up my iterations. So if that's going to be 0, I'm going to go equals this multiplied by my time constant. And I'm going to go F4. Oh, plus, not multiplied. Silly sod. I'm going to go plus. So now you'll see here. Now F4, for anybody who doesn't know, when you're wanting to hold a cell in position, you put your $ left and right. If you press F4, it is the lock key. It will just lock it, and then you can move on. Don't get me wrong, I know a lot of you will be like, "Yo, that's obvious." So all I'm going to do now is just drag it down. What you see now is we have that. I'm probably going to make that a little bit smaller, to be honest. So I'm going to go 0.01. My iteration processes then are a little bit better, and we can actually look at that a little bit more. Centered like that, and then I'm going to bring that back up. Right, so. Let's have a look. So simulated position. So this, what we're going to do is set up our position and also our velocity. So our dy by dt, our velocity. So I'm going to go our position. Well, I'll go sim position. And then I'm going to go dy by dt, and then I have my initial processes. Right, so how do we go about it? Particular easiest way of solving this is, what we'll do first is we will say, for the very first step in time, I'm going to say my initial conditions of y are 0. So we know that the position is there. In the second step, for my dy by dt, if we see there, we're going dy by dt is equal to sy, is equal to static sensitivity multiplied by initial input minus our initial condition of y, all divided by tau. So as a set out, it is dead straightforward to get used to and dead easy to do. Oh, apologies. So what I'm going to do is I'm going to go is equal to open argument. I'm going to say static sensitivity Now static sensitivity for the gain of the actual system is not going to change, so I'm going to say F4 multiplied by input, so in our case is U, and again for this that is not going to change, so I'm going to say F4 and close the argument, because remember the equation, yeah, that's fine. If you remember the equation, it is minus y all divided by tau. So what we do is come back again, and then what we say is, so it's closed that, so I want to do minus, I'll actually go there, because that's really where we're going to go as we're going through. And then I'm going to close that, and then I'm going to divide it by my tau value. For my tau value, I will set that to a 4, just to lock that in position. And that is my initial velocity of this running from 0 seconds. It is preloaded, so the energy is stated, so that's where this is coming from. Right, we now need to try and predict our next position. So in essence, where we've got to there, we've predicted this. This has given us our first steady state of where dy by dt will actually sit and land. Then what we need to do is to try and predict where that's going to be based on the next position in space. So our next position is based on our new position is equal to the former position of y multiplied, plus the time step, all multiplied by dy by dt and the value of 1. So what I'm meaning here is, if you look here, it's the number of where we're sitting, so it's former step. So that's all it's actually referring to. So again, let me just bring this out, just so I don't get myself tied up in knots. I'm very good at that. So I'm going to say is equal to my initial position of y plus, oh, god damn, hang on 1 second, yeah, so it's plus my initial position of y plus got arguments, time step, so it's the time step, the iteration step that we're taking, and it's just continuously recording based on that. And then, because that's in that value, we're going to say F4, and then it is, where we are now, so then it is multiplied by our position of y, our position of dy by dt, our velocity, and then close that. And let me just bring that down to there. Let's just check to see if that is recording as I wanted it to. Because the amount of times I've done this before, and then you look and go, oh hell, it's not recording like I wanted it to. So what I'm going to do, even though this is not properly, oh, I rushed that then. Anybody who doesn't know, when you've got a completed column to the left, if I want to populate to the same length of that, double click the bottom right where the crosshair occurs. So if I double click it, that will then present the solution for it. So what we want to do first is see if it's given us something that is workable. I just saw a question pop up. Apologies, I missed that question, Harry. Yes, of course, of course. Let me just come back. I'll zoom this in so you can see it, because I'm aware of the issue is it can be actually quite small. So if I leave that, that'll just give you an idea of where I've tagged that from. I don't know who was also in that same state of just trying to make sure that you knew where it was all going, but I just thought I'd point that out. So again, to auto-populate, just highlight your two areas and that lower cursor. When it turns to a black cursor, double click it and it will automatically populate the entire cell sets. I'm going to go Control. I'm pressing my fingers on Control. If I press down and then press Control and Shift, press up, on these are the arrows by the way, and then press left, I can now go to my plot and see what type of result it's giving me. So I'll go Insert, come back, and then we'll go to here. So my first initial thought is that is not like I was hoping. What I'm going to do is make my data sets longer. You look here, it's still on the rise. So I'm going to make this longer. I'll take this to probably, we see here it's starting to steady itself out at minus, so that's not comforting. So let's come back again, and then let's go and insert and take a look. So it's still climbing. Now I've obviously done something wrong. Has anybody idea of what I've been doing wrong? This can happen. This is just a blatant mistake. I'll explain to you. I've not tuned the values. It's all balanced. All it's going to do is just continue to climb, no matter what. The initial input is greater than what's the outputs on it, so it's never actually giving me anything. Everything's totally balanced. So if I now look at saying, right, okay, so our initial input on this will be let's say 5 newtons of force. So if I go 5 newtons, still nothing with it. But you know now that we've increased on the change. So if I go back, if I go 5 newtons, still climbing. Okay, so then if I say, right, then my spring stiffness, I want to make it stronger. So if I go, I don't know, 10, and then bring in a damping of 5. Oh, that's awkward. Just them moments where you think, yeah, I've definitely made an error there somewhere. Damn it. 2 seconds. Let me just figure out where that's coming from. Ah. Damn it. Okay. Oh, damn it. Right, I know where I made my mistake. Right, so we know that dy by dt should be a velocity state, yes? We know that we're passing a force into it, and then its initial velocity will be in there, and then we will, based on the system, it should degrade, should start to erode, should slow down, come to a stop. If you look here, because I was using F4 so much, watch this. If I go there, go there, go there, the velocity is assumed to be continuous. It's continuously going, so what it's actually doing is it's never going to stop, ever. So if I come back and then go to my dy by dt, my velocity speeds, and then come back again. Again, if you follow me perfectly, you'll know that you've made the same mistake because I made you do it. Once you've corrected that cell, bottom right, double click. There we go. That's more like what we're looking for. So we know that we've put an initial 5 into it, so it's going to give us that 5 out. So you put it in, you get it out, don't forget. On the gain of what we're saying, the input over output would imply that we're going to get something similar as it goes in and out. Our initial input sets to 0, so we know that that's right as well. There's a few things about this though, so we're going to plot a little bit more first, but there's a few things about this to really consider. I'm going to lower, I'm going to put on a greater spring. Now, in any type of spring system, if this is a door, so this just refers to its position, where it's sitting. So if this is a door, if I go 15, so if I raise that almost 3 times of what its counterpart for its damping is, what you'd imagine is that it should respond quicker. So 25. Where's my tablet? Ah! Silly sod. Done that wrong as well. So my tau, my God, I don't know how to fasten my shoelaces in the morning. So on tau, that should have been equal to C over K. To make sure that you believe me. My goodness, that is not a good start. C over K. That's much better. So in any spring state, if we make it much greater, if we go 45, the spring slams shut, as you'd imagine. The damper can no longer do its job, it can no longer support the output that it's been given. But if I then make it close to the damper, if I drop it to a strength of 6, what we see now is, if you look at the response, it's almost in the arc format. The response itself, there's very linear response to it. That would imply that the damper is dissipating the force incredibly well. So if I almost match it to achieve almost critical damping completely, and I go something as, I don't know, let's go 5.1. What we're really getting now on this response, the settle time on it is 6, apologies, that's my phone for eBay. Now we're taking 6 seconds to reach a steady state. However, that time it moves, that distance it moves, and the way it moves is very slow. So that tells us, as it's closing, it's one of them annoying doors that you'll see in many places where it's shutting. And in the end, you just want to push it to shut the damn thing. That's actually what that is implying with that. However, we do have a velocity. So if we're going to put this onto something, we could do with knowing how quick it's moving. So let me copy that. If I paste that in, so the velocity is recorded for meters per second. So it's moving. Because we're in seconds, this is moving relatively quick. If you look between, you've got a steady resting state to 6, and so this is 6 seconds. And it moves 5, so between there and there, let's have a look. You could say what? On the initial response of it, it could be moving, what, 2.5 meters per second, based on where the intersection point is, roughly to where 1 would be. I'll stretch that out, it should give me a little bit more. Oh, no it didn't. When you actually look at it like that, you kind of go, is that going to be an ideal for a scenario? So, okay, so then you say, then let's incur a greater stiffness, and let's see if we can incur a greater speed for it to shut. So if I go up to something like 8. Now we know from that, once we're up to 8 as a spring stiffness, it now goes much higher. Now if this was designed for a door, you'd then start to really think about, is this configuration moving too quick? So quick that if it's shutting a door, is it going to smack somebody in the back of the head as the door actually closes? Interestingly, when you're designing these, there actually is a fire door standard that you must follow. Now, as a side note, this used to be an assignment that we used to run, that students needed to design this and go through it. I did have one student who actually worked at a company who designed and built fire doors. He was actually telling me that fire doors, depending on where they are designed to shut at a particular rate and a particular speed to ensure that if there is a fire, the fire service can roughly predict how the actual building fire will spread. It was information to me. I must admit, I never knew that. But as a example goes, it's an interesting one. So, lastly, I say lastly because I want you to have a go at this as we're on here. I'm probably not going to work through this bit because this bit is worth you having a go at. We've still got a little bit of time yet to actually really get used to navigating his way around this, but there is one last thing that I wanted to examine, and it is the exact equation. Again, these notes are on Blackboard, so you can download this. So the exact solution, what this will do is it will present you with, where is it? There it is. So this exact solution, what this will do is it will present you with a solution which looks like, I have in true Blue Peter fashion, I do have one I made earlier. 2 seconds. It will present a solution which looks like that. Now the exact solution for a first order system gives a nice response. You have the exact and you have the simulated. The simulated, because of the iterative response, every single system uses an iterative response, but the exact solution allows a difference between it, and it's almost very similar to the error that you will find in most simulation models. What I would say is, I want you to have a go at actually making that into here. I'm not going to leave you for too long at it, but I want you to have a go at it. It's tricky to get working, and it's tricky to really figure out how it's all applied. Again, this is just a bit of a warm-up to simulation. This is typically how the module is going to work. We're going to take equations, when we're going to apply them, this will be dynamic equations. Just to feed back onto a comment earlier, it won't be necessarily through iterative processes. It may be variable time steps, which some of you may or may not come across as of yet, but yeah, it is going to be one of them that we approach. So what I'm going to say is, I'm going to give you 10 minutes to have a crack at putting this together. Oh no, we'll go 15 minutes to have a crack at putting this together, and then in 15 minutes I'm going to take you through some of the best ways to solve this in a system like Excel, to actually find a solution for it. Then once we've done that, we're going to put these graphs into a presentable format, because this is not really a presentable format. If this was put on a project, on an assignment or anything like that, it would prove to be a bit naff. So that is not the best way to present a sorry, my mouse went dead then. That is not the best way to present a graph, and I'm going to take you through that, and then we're going to call it a day. So as I said, I'm going to give you 15 minutes and counting to actually get this together. If you're looking for these notes, they're on Blackboard, and they are under Module Material, MATLAB and Simulink Notes, Tutorial 1, First Order System. So have a go, and as I said, we'll give it 15 minutes and then we're going to come back to it. So if anybody's wanting to physically ask questions, you're more than welcome to it. I'm just going to pause the recording. So our time period's now passed, and let's take a look at solving this and how to approach this. The reason I made you guys take a look at it, let me just open that back up. I had to close it because I had to put these notes onto Teams, and it just was not happy with taking a bit of a snapshot and putting it straight onwards. So one of the most frustrating things about this equation, it is just not clear about exactly how these things are used. Well, I lie, it is clear, but it can be a bit confusing, and I've probably confused things quite a bit, to be honest, because I've misnamed something. Really, in here, what I should have done is where my H lies, to make sure everything's complete properly, I should have really called that T. So then T becomes my time step, and H becomes my oh, apologies, wrong way around. I should have named this T. So then this becomes my time step, and this becomes the relevant time that I'm sitting at. So that is my mistake. So if you got annoyed and it's not working, you're getting very frustrated, that's my fault. So if we come back on and we look onto the equation itself, using exponentials, for anybody who's not used them in, I said ANSYS, for anybody that's never used them in Excel before, EXP, and then you open and close arguments to give you what you're after. Now, I've seen this particular thing solved loads and loads and loads of different ways. If you're confident with how you're, it's not really coding, but how you're building this equation into something like Excel or even MATLAB, that process of building it can be a little bit hit and miss. It can be a little bit all over the place. You can come along and go, well, not still 100% clear about what I'm looking at. So, what I have seen people do in the past is extract elements from it. So solve that in a separate cell. Then actually solve that in a separate cell. Add all the individual cells together and then build it up that way. It's one way of doing it. And there's nothing wrong with that, by the way. It does work incredibly well. For me, I've always preferred to have it all contained. But I've always been, personally, I've always been quite good at just keeping an eye on how these things are put together. Let me put that like that. I'm going to try and keep these separated just so that we can see them. I think I've just had a question come through. Let me just see. Oh, apologies, member of staff. So we got that exact solution. This method that we're going to use for iterations like this works with everything. So for those of you who are doing mechanical maintenance with Ted, this process that he does, this is very similar that he'll be doing again and again. For those of you who do engineering tribology with our prof Ian Sherrington, Ian will be looking at lubrication regimes. He uses the iterative process there. It's all very fundamental, the process of doing it. Building these bloody equations, though, can be a real pain in the backside sometimes. I say sometimes. So, let's go exact. Now the beauty is with the exact, I quite like this, because the beauty is with the exact is it's very similar to if you're doing hand calculation, through to simulation, through to your closing validation. So we could kind of treat this similar to what you'd be looking for in any particular validation. The output it gives us, we can try and assess and review what the hell's going on and why it's different, and even propose what the differences are. So, big steps. Equals. It's a big one. We're going to go static sensitivity, F4. Look at this, S never changes. We're going to go multiply by our initial input. Again, initial input never changes, F4. We're going to multiply that. Now when you multiply that out, now we've now moved into the argument section. Now on the, or brackets. I know I'm in arguments just because when you're coding something, when you're coding any type of controller, or if you're coding through C code, anything like that, it's known as arguments. Don't know why they're called arguments. I'm sure someone can fill me in on that. So I'm going to open up brackets and go 1 minus. Again, for that exponential, I'm going to go EXP. The system recognises it as a fundamental tool for functioning, so I'm going to open up my argument. Now looking at this, we've got a minus t. So I'm going to go minus, come over to here. Interestingly, for the exact fundamental equation, that is the only variant. Look throughout the actual system. We've got a start of y and we've got a finish. This goes back to Newton's laws for motion, and it is a different way of solving it, but it gives us this really nice comparative that for this session, just for this session really, it's really nice to really review what's going on, and this really spells out the limitations within simulation, hence why I wanted to do it. So, come back in, we're now onto that T, we're going to go all over, tau. This is our solid variable box, so I'm going to go F4, hold that in, close the arguments, and then close the arguments. So now we're actually into the SU, we're into the static sensitivity, where the S multiplied by our input of U, and we're actually closed around this bracket here. From there I'm going to go plus. Now we've got the Y0. Now you could take this from 2 points. You could either take it from there and lock it to that position, or lock it here. Now because we're talking about a continuous variable, and to make sure that when you look back you don't go, the hell have we just done? Why did we actually put that in there? We will hold it in this state. So I'm going to click there, and I'm going to click F4. That then holds that in, and then I'm just going to scroll that along a little bit. I mean, I've seen some who just simply copied this now, copied and pasted it. But I'll go EXP, exponential, open that argument, and again, I'm just doing the same thing. So I'm going T, whoops, missed the minus, that could have been embarrassingly wrong, again. Then I'm going to go all over my time constant of tau. Again, same thing as before, it's a constant though, so we're going F4. I'm going to close that argument, and if I'm not wrong, I think that is our built equation. We'll certainly find out anyhow, because when I move down, it will either go batshit crazy or work like I wanted it to. So again, into the corner, double click, and you look here. We have 0.07, 0.08. We've got a slight change. They both start at 0 because we've initially put that in manually. That's all we can say. That is what we know. But this implies that there is a difference. So let's take a look at that difference. Let me bring that back a little bit. What I'll do first is I'm just going to build my simulated state. So let's go into the simulator state and let's build that in. And what we want to do is we're going to add some axes onto these. I'd like to get a quick layout. There's a few ways. I'll probably do a quick layout. Let's have a look. Is that going to be right? I don't need. Well, no, I'll leave that in because I'm going to add more in. So this is going to be position. And then this is going to be time, and as we know, this time is measured in seconds. So we know that this is our relative displacement of where we're sitting. So that's where we've come out from. Now, that's our simulated response. Now, what I really want to drag into this and really want to spell out, because there is this huge misconception about simulation that it'll just, you don't have to do particular prototyping anymore. I do know that we've got industry guys who are actually sat in this audience, in a lack of better words, which sounds weird to say, and you guys will be well aware of that simulation is far from being in a position of being able to do away with prototyping completely. This just drops the inaccuracies that could occur. So it minimises that error between between idea through to prototype or modification. So we got these 2 points, and on here what we're actually looking at now, this is one of the reasons that a few people I've met at conferences really get annoyed with Excel. Now, it's purely because in between each one of these points is a point, and then what Excel will do is it will turn it into a curve. That can be quite misleading. So really what we should be seeing is line to line to line to line, like a bitty response, if you will. What we'll do now is I'm just going to make that a little bit more blatant, so I'm going to go 0.1. Yeah, I'll go 0.1, and you'll notice I've dropped that quite a bit, so no, I'll go back to it. It seems a little bit, too many zeros there, I think. So I'll stay with that, and now what I'll do is go down to my exact, press Control, go to the bottom, press Control, press Shift, press up. I'm going to copy. A student showed me this a few years ago. I had no idea. So I'm going to come in, right click and paste it in. Now, provisionally of looking at that, you kind of look and go, wow, yeah, it's pretty good. That is pretty good. So let's just measure. What I would say is let's just measure between, let's have a look, where are we sitting? Let's just get to there. Where the system just is about to go steady. So I'm going to go insert again, come back and go to there. Do that. I'm just going to move to the top. And I'm going to paste that in. So now we've just shortened the time down quite a bit, in fact. Then let's come back again. So I'm now just looking to match against that record. So I'm going to come from here. I'm going to copy. And I'm going to paste that straight in. See again, it's still. If you actually look, there is a difference between it. Now we can calculate that particular difference between it by simply figuring out the error of the two. And if we can figure out that relevant error between the two, we can actually try and plot that. So the error percentage. Now it literally is, sorry, very stiff back. So it literally is our simulated position minus our exact, all divided by our exact, multiplied by 100. So I'm going to go from a state that I know, that I've been doing it. Here, there's not going to be much there. And we've really put that value into it. So I'm going to go open arguments, whoops. I'm going to go U. I'm going to go minus U. I'm going to go divide by all of U. Yeah. I'm going to go divide by U. Close that. Multiply by 100. Bring that down. I've taken it incorrect there. So I've gone to there. Whoops. So I'm then going to highlight all of this, and this is going to plot me the differences between the two. So what we can see with that is that the two values are at the highest inaccuracies from the start. Then as it's racing up, it's very similar to what would be the velocity response. Once it reaches a steady state, they do become very close, but this would suggest that the highest points of error are around this arc. So if this would suggest that the highest errors that are around the arc, it would mean this methodology of using iterations is going to present a truncated response. It's going to present me with a solution which is always going to be, in lack of better words, slightly stiffer. It's always going to be that little bit more solid as a response. When you open up any engineering software package, when you open up any thing, any simulation, if you open up any research journal and you look at what people have produced, when you look at anything that people have been presenting, you'll notice one massive thing. They always, but always, talk about the error that's been generated between the two. When they're talking about the error, this is what they're talking about. Rather than me just going, yeah, everybody, we're going to look at the error, I wanted us to work through that problem. I wanted us to work to see that solution. So when if you're a keen user of COMSOL, MATLAB, ANSYS, SolidWorks Simulation, CATIA's Abacus, they all present that we've got accuracy down to 99. I think at the most impressive I've seen at the minute is 99.97% accurate. What they're actually referring to is it means that they've got a solution, an iterative or a meshing solution, which it does something extra. It minimizes this relevant issue. So my next thought would be just ignoring the response of it, but if that's true, that means if I make that to 0.1, it means, look, don't know how well you guys can see this. Let me just see if I can zoom it right in. If you look now, you see the arc, it's more blatantly obvious. Now the reason that is because my iterations between each recording have been doubled. So this iteration here is even less. So there are less points of velocity that we've been predicting to actually give us that result. What we're ending up with is a far stiffened response. Now I can imagine what a lot will be thinking. Okay then, what if I go 0.00000001? You go, oh yeah, oh, look at that, oh, shoot. What we end up with now is where the equation becomes unstable, the accuracy is way too far out. We've actually not found the ideal way of simulating these. We've not been able to converge our result. Convergence is something else that we will be covering through this. The reason I couldn't discuss this much yesterday on the MATLAB session was purely because in MATLAB all this is automatically done. It's all hidden in the background. And if you are curious with MATLAB, again, everybody's welcome to both. If anybody's curious about the timetable, the register, by the way, I've already taken it. It's alright, so don't worry. But the real learning side of this is, if I go that level of zeros, okay, let's see if we can get something that looks a little less nut job crazy. So let's just go to something still very small, but something less. Right, so this then becomes another big issue with simulation, and the reason that we must converge. You saw, if we look back at that solution, you can see how it's responding. It almost looks like it's the initial points of the system responding. So at present we are at 1,461 lines. Let's just go a little bit further. Now I do know, you look now, we are still miles off the actual solution where we need to be. So let's take it to 10,000 lines. I think we're going to get limited. I think we're limited at 60. Don't worry, we're not going to 60. But you look, we're still changing. However, you look here, the exact solution, the exact solution is still outside of it. So my point is often when you're building a simulation, when you're building a system that you're predicting, often a lot of people can go, well, I'll make it, in meshing this is the most common, where everybody goes, it's okay, I'll go super fine. If you go super fine on a particular, or I should say extremely fine, on a particular simulation, when you run it, what you'll actually do is find it crashes. The amount of people I've seen sat there, and I'm not just students, the amount of people I've seen sat who go, why when I run it is it crashing? It's crashing because that is what they're doing. What they've actually done is each system that you're building, When we get into meshing a little bit more, I'm going to show you how the stiffness matrices works and how it's simplified as it's going through. This simplification process, if it is too big, it doesn't know where it's simplifying, the equation becomes unstable, and this is the type of response that we get. So this module is really about not doing this. This module is about thinking about what we're doing, thinking about the differences, but not going over the top, but really thinking about our responses and really considering, one, how are we going to verify what we're getting? Two, once we've verified it, is it right for our criteria? So let me just come this back in. I'm just going to add this one back in because it is one that I do quite like, so I'm just going to add this back in. So when we add our velocity in, is it moving so quick, in a door example, is it moving so quick that it would smack somebody in the back of the head and probably shatter their skull? At this level of speeds, provisionally, I probably wouldn't put this together just because the response of it is quite aggressive, very aggressive. So obviously, if you're designing something like this, a great one for this is the motorsports students, probably aerospace students. You guys will have come across this quite a bit. Where you're designing a spring and a damper system, you need to get that input design, you need to get that formulation between it, and you kind of go, oh yeah, this is my criteria because of this, and this. My inputs will be this, and this. And what this module is about, and what it's really about spelling out, is setting up good sims. Setting up stuff that if you took this to the boss, if you took this to the teammates and went, look, I found this, they can look and go, yeah, I totally get that. Because it's all about the project, it's all about whatever it is that you're simulating. Yeah, so that is a nice warm-up. If anybody's really keen to have another crack at building their own up, as I said, on Blackboard. Whoops, I think I have another question. No, I don't. As I said, on Blackboard, there is the second order systems on there. You're welcome to have a crack at that, have a go with that. This week was just about getting used to the approach and getting used to some of the big things. So, granted, I didn't tell you from the start exactly what we were really, some of the key elements that we were learning about. So the first one for me is the accuracy of what you're looking at. This is just a very simple equation done by Euler's iterations, and we're just using that as a basic process. When we're moving more down the line, we're going to drop more and more detailed problems into it. So we're going to go from something simple, like looking at variations of wheels, looking at the impact of torque, and looking at that changes. So into next week's MATLAB session, I'll be using Sim Multibody to build up the wheels. Into next week's SolidWorks simulation, I'll be doing the exact same model process, but in SolidWorks. We'll be getting some results that are very similar. You will, between the two sessions, whichever one you want to look at, you're welcome to it again, and I'm always open for chats if anybody wants to know more detail. There's loads and loads of exciting stuff with it, but what we'll be doing is just looking at torque and the influence of mass and the influence of gravity, because we're going to try and smash a bit of a myth as well of that gravity plays such a massive role on torque when it's being driven by a motor. We're going to try and build it in. We're going to do some maths to actually verify it. It's basic torque outputs, but we're going to predict what we're getting, and then we're going to generate from there. Apart from that, I hope this session's been just a slow introduction to what we're going to do. I didn't want to just bring you all in here and kind of go, right everyone, we're going to do this, this and this, and get you all feeling a bit annoyed. A post about some of the graphs and things that I've just got. To that, these are, in fact, what I will do, by the way, after this, I will stick this onto Blackboard, and I'll probably stick this on Teams as well, because I know some of you guys are struggling to get onto Blackboard and get that sorted. So I'll stick this onto Teams as well, and you can download this for yourself and see what I was putting together and just clarify from that. Again, I hope this has been a nice introduction. As this year goes on, it is going to be very different. It is very different. It's a whole new world, as everybody keeps bloody telling me. What I want to try and do is get a real benefit of some of these awkward scenarios that we've all been put into. So I'm going to try and do this. If anybody is not comfortable, please let me know. I'm more than happy to try and help. And if you as a group are not happy with this and this level of approach and having this interchangeable options, I'm also open to just going back to the conventional way, which is just to stick with MATLAB. I just wanted a little bit of more insight to even more what we're doing, and then we're doing less about software and we're concentrating more about the techniques and solving them particular problems. Other than that, I'm just going to stop this recording. 2 seconds.